Beautiful first slide.
Which I, of course, downloaded from the internet. So each of us, of course, has a strong feeling that melts percolating somehow, penetrating somehow through the lithosphere. They should weaken this lithosphere. So this is our intuition, and this is what we think about it. But I'll try to elaborate a little bit on this intuition and try to show that sometimes some quite counterintuitive conclusions can be derived. So I would like to speak about melt-induced weakening of the lithosphere, essentially about reduction of strength of the lithosphere under the action of percolating melt. So it's a kind of theory which starts from another downloaded image from the internet. So if you search for lithospheric strength, we all think we know what lithospheric strength is, but in reality it's quite misleading thinking. So probably lithospheric strength is not such a well-defined property of the lithosphere. So if we type here lithospheric strength, we get a bunch of these Christmas trees. So now let's try to think about what lithospheric strength is. Is there a difference in between lithospheric stress level, for example, and strength of the lithosphere? So looking at this Christmas tree, we do not feel like there should be a difference. So since this is more or less lithosphere is stressed, and then this envelope is showing, how strength and stress in the lithosphere are distributed. However, let's try to quantify both of these quantities. Let's take an elementary volume of the lithosphere and then define what is the long-term stress level in the lithosphere. So we have a volume and we have period of time through which we are quantifying stress level in the lithosphere. So stress level, deviatoric stresses can be represented by second stress invariant, and then we just, integrating this quantity over volume over time. So this is what is stress level in the lithosphere. So on the other hand, what is long-term strength of the lithosphere, of the same volume of the lithosphere? So my proposed definition is the following. It's amount of work that we have to spend to deform in a reversible manner this volume of the lithosphere to a unit strain. So how much work needs to be done to have certain amount of irreversible deformation, because we do not care about reversible deformation. Since it's as much energy as you put into the system, you can retrieve from the system. So you do not do irreversible work. So in order to quantify amount of irreversible work, we can use energy dissipation. So this is telling us how much work is spent for viscoplastic, for example, deformation, which are reversible deformation. And then we make an integration again through the volume through time. On the other hand, second quantity that we have to quantify is amount of irreversible viscoplastic strain. And this again, double integral through the volume through time of this quantity. So, and we do care about accumulation of this viscoplastic deformation. So for us, if we squeeze viscoplastically and then stretch viscoplastically, amount of deformation will be non-zero. Therefore, we are using here second invariant. We are not using really deformation, viscoplastic deformation tensor. So it means that we really do this, first we compute second strain rate invariant, and then we make this integration. So if we divide one over the two of over the double of the other, we get effective strength of the lithosphere. So amount of energy spent for unit of irreversible deformation. So by definition, these two quantities are non-equal to each other. They can be equal sometimes, but in general, as you see, these are very different quantities. And then one can actually expect very significant differences in between those quantities. So here we come to two definitions. So stress level is, by definition, not equivalent to the strength of the lithosphere. At least something is resolved. Then next point is the following. So let's imagine we are dealing with melt percolation through the lithosphere. For example, to form some broadly distributed magmatic activity. Of course, this melt percolation through the lithosphere is episodic, so we can consider conceptually. And then second point which we can consider, of course, strength of the lithosphere, brittle plastic strength of the lithosphere in the absence of melt is, corresponding to these brittle yielding conditions. So we are not even speaking about ductile strength, we are speaking about brittle strength. So we have like ambient strength plus friction coefficients time pressure. So at the moment of time when melt is moving through this lithosphere, we have to modify this yielding condition to account for the melt pressure. So, and then one possible way to do it, instead of multiplying friction coefficient to pressure, we multiply it to the difference between this pressure, which is now defined as total pressure, so means that the pressure and an effective pressure in between fluid and solid with zero proportion minus pressure melt. And this is our yielding criterion. So, but only for the moment when melt is moving through the lithosphere. Now we can just try to modify this expression so that it looks like the previous one. So we are introducing this factor which is corresponding to the reduction of strength of the lithosphere at the moment of melt percolation, which I call here lambda, which is 1 minus pressure melt over pressure total. So it's my melt-induced weakening factor. Now the question is, if our lithosphere is subjected to repeated melting propagation episodes, which are very short-lived, and then we would like to derive this lambda factor for the very extended period of time, what will we get? So imagine this happens within 1 hour. The rest is lithosphere is quiet, there is no melt in the lithosphere, and then it's strong. So averaging, if we do time averaging, we will always get value which is close to 1. So since melt will be absent most of the time in the lithosphere, this ratio will be close to 0, lambda will be close to 1. Then prediction will be this lithosphere will not deform because our melt weakening parameter is a time average quantity. But in fact, if we go to these two equations, what this equation is telling us, that strength of the lithosphere and lambda is a function of this strength, is not a time average quantity, it's a strain average quantity. So if we analyze and take magmatic and amagmatic episodes with their respective strengths, and we analyze condition for the integrated energy dissipation and integrated strain, what we will realize is that, first of all, effective strength of the lithosphere is a strain average in between strength of the lithosphere during magmatic episodes and strength of the lithosphere during the amagmatic episodes. And then our total strain is the sum of magmatic strain and amagmatic strain, which implies the following. If most of our irreversible strain, viscoplastic strain, is happening during very short magmatic episodes, strength of the lithosphere will be equivalent of the strength of the lithosphere during these magmatic episodes. So strength of the lithosphere will be equal to the strength of the dike and not to the strength of the amagmatic highly stressed block. It's quite a counterintuitive prediction from analyzing this definition of the strength of the lithosphere that I simply made. So then this is our lambda, long-term lambda property. So this weakening factor, as you see, lambda magmatic, which is much less than 1, times strain magmatic divided by strain total, plus 1, which is lambda for magmatic episodes, times irreversible strain for magmatic episodes divided by strain total. So if there is no magmatic irreversible strain, lambda melt should be equal to lambda magmatic. And this is what our dissipation-based definition of the strength is giving us. So if we agree with this definition, we will have to agree that strength of the lithosphere is not a time average quantity, it's a strain average quantity. So if all of our deformation, irreversible one, is happening even in seismic modes due to the, for example, rupture propagation along the dikes or quakes associated with these dikes, strength of the lithosphere will be equivalent to the strength of a dike and not to the strength of the strong block. So, and this is what we can do, what we can try to do numerically. We load our lithosphere with elastoplastic with some strain rates. And then once a year, we will be shooting one dike somewhere at orientation approximately corresponding to the plus minus 15 degree from the vertical, which is corresponding to dike's orientation in the area of extension. So what is happening in between dike's episodes? And dike will be active and weak during 1 hour only. So this is so-called seismomechanical models, which allows to also resolve very high velocity, so you can have both slow loading and rapid rupture. So then what is happening in between these magmatic episodes? Lithosphere is deforming, but it's only deforming in elastic manner. We do not accumulate any inelastic deformation. Then, when dikes is shooting, we have lots of inelastic deformation, mostly concentrated along the dike, but the dike is weak. Therefore, our irreversible deformation is accumulated under weak conditions. So if we then make this application of these two formulas, what we will see is a big gap in between stress level in the lithosphere averaged through time and space, and strength of this lithosphere obtained as a dissipation divided over the inelastic strain. So, means that lithosphere can be very stress level, 100 megapascal, but at the same time, because of this ongoing process of magmatism, which is short-lived and very local, so it was local in space and time, we can still have property of the lithosphere, which is extremely weak. So gap in between these two parameters can be almost an order of magnitude. And our effective lambda melt, which is computed here from the effective strength of the lithosphere, can be also very small, so much less than 1. Because it's, once again, as expected from the theory, is a strain average quantity. So now I will be speaking about numerical implementation of two-phase flow, which will have almost nothing to do with the remaining of the talk. But since we are on this two-phase flow workshop, and since it has direct relationship with this melt-induced weakening, I will speak a little bit about numerical implementation, how I see it from the point of view of a modeler. So, and then from the point of view of a modeler, since modelers, they have lots of experience in solving Stokes problem. So the wish of a modeler will be, I take my Stokes code and I do minor possible modification to have two-phase flow implemented. So, and this is my kind of first desire. So little modification. And this is what you could do with the set of equations that I put for you here. So first of all, total momentum conservation equation is the same as in case of one-phase Stokes. We are dealing here with total pressure, we are dealing here with total density, and we are dealing here with deviatoric stresses, which are constrained for the solid velocity frame, because this is the only solid which is actually creating these deviatoric stresses, since fluid is of low viscosity and does not contribute much. So we are dealing here with the total parameters, means with the parameters of a mixture. As you see, it's a standard Stokes equation. Then mass conservation equation of the solid. It's our usual mass conservation equation. Both solid and fluid here are considered incompressible, but in the right part, instead of 0, as for truly incompressible, we have term which is reflecting viscous compaction, or better to say viscoplastic compaction. And here we are dealing with bulk viscosity, or as Rich suggested in his textbook forthcoming, hopefully within probably a year or two, it's a compaction viscosity. So it's a response of the system for compaction-decompaction process, which can be, in fact, some nonlinear parameter depending also on plastic yielding or on brittle deformation. So this is what appears in the right part of our continuity equation. Then fluid momentum conservation equation is a standard Darcy, so nothing really special. Then mass conservation of a fluid, it's divergence of Darcy velocities. And then in the right part you see the term which is just the same term as here, but without minus. And then matrix porosity evolution, which is actually describing changes of porosity with time as a function of the difference between total pressure and fluid pressure divided over this compaction viscosity or bulk viscosity. So what I consider quite essential for implementations of governing equations for two-phase flow in case of the lithospheric deformation is to consider brittle plastic deformation. Specifically because of this criterion and because of what we have seen before for the strength of the lithosphere. It's critical to take into account that strength of the lithosphere is a direct function of pressure total minus pressure fluid. This is also the reason why I keep pressure total and pressure fluid as two parameters in my set of equations. So I really want to have them explicitly. I want to compute distribution of these two parameters, and I want to be able to compute difference in between them, which is feeding back into the yielding condition for my rocks. So friction coefficient is from 0 to 0.85 for the confined fracture, which means pressure total bigger than pressure fluid. Fracture is confined, it's expelling fluid, and strength is described with friction coefficient less than 1. And then for tensile fracture condition, when pressure total is less than pressure fluid, instead of applying Griffith's criterion, what I use is simply friction coefficient equal to 1. This gives us orientation of shear bands vertical under extension. So it's a simplification. I do not give here full Griffith's condition, but I just use friction coefficient equal 1. So and this is the set of equation which is in principle trivial to implement if you have already working Stokes solver. All you have to do, you modify your right part in the continuity equation, and then you add 3 more equations. Some people prefer to use, to reformulate mass conservation equation of the fluid to obtain solution for pressure fluid and eliminate Darcy velocity. But from the point of view of efficiency of calculations with using direct solver, you're not gaining much. You do gain if you want iterative solution. It seems that this elimination of Darcy velocity would make solution for pressure fluid more easy, and this solution is fully equivalent for obtaining solution of Darcy velocity by post-processing, because Darcy velocities, in principle, you can recover them by knowing fluid pressure. So, but this is a kind of question of test. What you prefer, easiness, then you just implement all 6 equations in 2D. If you want to do probably 3D and iterative solutions, then you do Stokes equation and continuity for the solid, and then modified continuity equation for the fluid. Then you will have, instead of 8 equations, you will have 5 equations only. So method of numerical solution. I'm still promoting the same, how I call it, simplest method, which is combination of staggered finite difference and marker and cell technique. So this is the staggered grid where you can implement all these equations very naturally. So velocities are sitting in respective staggered points. Pressure, fluid, and solid are sitting in the same point here in the middle of the cell. And then respective strain rate and stress component are sitting in 2D, either in the corner or in the middle here. So normal components are here, and then shear components are there. And also, obviously, densities have to be defined in the velocity points, because these are the points where Stokes and Darcy equations are formulated. And the same is, of course, for permeability, because this is also where you solve Darcy equation. So, and markers are used, as in case of pure Stokes solver, for transportation of all material properties, including porosities, including permeabilities, and including also stresses, if you have elastic approximation of your solid, or viscoelastoplastic approximation of your solid. So interpolation between markers and nodes is done in bilinear fashion, the same as I was describing in this textbook. So nothing changes really. It only depends on you whether you use more local interpolation or wider interpolation. The wider interpolation is actually seems to be producing less localization, but it's more stable and produce more accurate result, as work of Dave May and Thibaut Duret has shown. So numerical algorithm, one possible algorithm is described in the PhD thesis of my former PhD student Diana Demkova, and essentially it's quite a standard interpolation of physical properties from marker to nodes, solving the systems of equation, calculation of stresses and strain rate, applying plastic yielding criteria, taking into account fluid pressure weakening. So here is where we are taking into account difference between total pressure and fluid pressure, calculation of porosities evolution, calculation of time step, solving temperature equation if it's thermomechanical problem, and then interpolation of properties to markers, temperature to markers, and advection of markers, and this is the algorithm. So quite simple one, and it's a slight modification of the thermomechanical algorithms typically used in single-phase flow codes. So now numerical example. I have only one numerical example, which is about this melt bend's inclination. So here, melt bend's inclination is something like 15 to 20 degrees. As you see, it's a higher porosity melt bends. So they're quite similar. They have quite similar inclination compared to what is measured experimentally. However, of course, this solution does have some intrinsic problems, and the problem here is that melt fraction inside the melt bends is not limited by disaggregation limit by 20–30%. It goes up to 100%, and nothing actually in the physics that I described here in the equation precludes this increase in the porosity. So, which implies that our equations are probably good in reproducing the shear bend angles, but they are not good in reproducing some other features of the of this melt bends evolution. So something is still missing from the physics. Then, by comparison to other models, this viscoplastic model that I'm showing here show quite similar inclination of the shear bends compared to viscoelastoplastic model that Tobias Keller published in his PhD thesis. And then also it's the same inclination of shear bends as Holtzman and co-authors published in their paper. So prediction then from these models is that it's a frictional interactions between grains which are governed by this type of yielding conditions are defining this inclination. So this inclination will depend on the friction angle. Most of these bends, since they are sucking in porosity, are tensile bends, so they are corresponding to friction coefficient equal 1. But sometimes you can also see some shallower bends which are expelling porosity, and those are corresponding to a friction coefficient less than 1. How good is this model compared to what is defined experimentally? It's difficult to say because we need really detailed comparison. I will show you here one experiment with large strain. No, it does not look like it wants to show anything to you, but yeah, it's probably wrong desktop, but the trouble is that we will do it on fly, so does not. Command C. I'll do it brute force. We'll just copy paste in one slide result of one single stage of experiment, and then to.
I guess it's the extended desktop. If you move on one side or the other, you should.
Yeah, the trouble is it's just full screen, and then oh no, this doesn't work. Okay, anybody who is interested can come, and then I can show it, or probably if you can help me, then so all I want to is to show, like I was using typically duplicate screen, but this does not seem to work. So it's a screen display, and then arrangement, mirror display. Okay, yeah, hopefully you will see it. Yeah, let's see. Yeah, okay, yeah, excellent, thank you. View, slideshow. Lucky us. Okay, so these are strain markers, the shear bends porosity. Look at the evolution of porosity through time. I am deforming to relatively large strains. So some of these shear bands, they are rotated. They get rotated really. But then as soon as they get rotated, they start expelling melts. Because they're in the wrong position, in the wrong orientation, they becoming confined, they expelling melts, and new shear bands are forming because of that. And you can see how these new shear bands are shooting. They are starting to suck melt in. So there is some interaction between the old shear bands and new shear bands. Of course, this is a numerical result. It has been, something like that has been visualized also by Holtzman. He was showing that there is some kind of loops in melt flow from the older shear bands into newly forming shear bands. But it needs probably direct really imaging from this melt bands deformation experiments to understand whether these melt bands, they just stay as is or they indeed, you know, rotating and reforming. So in the end, of course, after very large deformation, we still see the same melt bands inclination, the same 20 to 15 degree. But it's just formed by repetitive cycles of melt bands formation and restraining. So what we see is that our melt is always traveling through the marker, through the matrix. As soon as, you know, shear bands rotates into, toward the steep angle, melt just escape from the shear bands and go into the new one, which is forming by the same type of frictional instability. So this is the result that I was hoping to show you. So now let's come to the presentation. No. Okay, exactly. Geodynamic implications. This is the best part, of course. In fact, this melt weakening has been implemented in many previous models. So we just was calling this strain weakening, for example. So what we did in 2007, when we were trying to understand how these big ultramafic intrusions, which are penetrating low density crust, could be formed. So, and it's quite amazing. We have like peridotitic intrusion in the middle of low density crust, which has density deficit compared to the intrusion itself, something like 600 kilogram per cubic meter, and then you start to wonder how, if we have this concept of natural buoyancy level, why should our intrusion just go so high, almost to subsurface through rocks which have obviously very different density. So, and this is, by the way, one of the quite, you know, remarkable platinum deposits. They have platinum crystals as big as my fist, and they found this in alluvial deposit here in the middle. So there is a river coming outside of this ring. So now what we do is we try to answer question why high density intrusions are coming through low density crust. So this is our simple model, and by the way, this is a single flow modeling. So as I told you, I have only one example with two-phase flow, which are shear bands experiments. So here we have like partially molten region, viscoelastoplastic lithosphere. There is some magically forming magmatic channel, which is ending up in the bottom of the crust. So which is characterized by hot at temperature, so it's like a feeding dike. And what I want to understand where these melts will go. And as you see, these melts does not pond because density of this partially molten magma is in the middle, somewhere in between density of the crust, of the lower crust, and density of the lithosphere. So natural buoyancy level is here. Nevertheless, this stupid magma goes straight up to the top of the crust and then start to form some kind of a funnel-shaped body there. Of course, it's of course a interpretation, like two-dimensional interpretation of the shape, because we have infinite second dimension. So, and then it's just generally freezes there. So it does not point at the natural buoyancy level, it completely ignores natural buoyancy level, instead it just rises up. So the question is, why does it do it? Not only in nature, but also in numerical experiments where everything is controlled, including gravity, so it's not the moon which is, you know, driving this intrusion up by gravitation. So principle is the same as in case of iceberg. So head of the iceberg, which is sitting in the low density air, is stabilized by deep roots of the iceberg, which are sitting in higher density crust. So here we have like soft surrounding, rigid iceberg. Here we have liquid iceberg and rigid surrounding. So there is not enough energy for the intrusion to emplace here because crust is too cold and too strong. Therefore, it breaks the crust and then come to the higher levels where strength of the crust is smaller and where emplacement work can be done because of the available potential energy. So we have to consider this system entirely. So from the bottom of the lithosphere, where we have appropriate density difference, which is 150 kilometers, for example, thick, and then we have like 100 kilogram density difference between this magma and the surrounding, which is stabilizing top of our iceberg above the natural buoyancy level. Of course, it's only the function of the rheological property of the lithosphere and magma supply velocity. So if we make our lower crust less strong or less cold or more ductile, what may happen is that we can pond at natural buoyancy level because surrounding crust will be able to deform in response to the magma supply. So it's really viscosity or rheology of the crust and rate of supply through our magmatic system of melts into the crust, which are controlling where it will be emplaced. And important point is that when we are speaking about movement of magma through the lithosphere, we will have to also consider these magmatic roots much below the crust, because this is where the whole balance of pressures and forcing is achieved. So now if we do some kind of classification of different bodies forming in these single flow models with applied strain weakening, so strength of the material is decreasing with viscoplastic strain, we see that we can have like dike-like bodies, balloons, also some funnel-shaped geometry, also eruption of material close to the surface, this magma flow, and everything is more or less controlled by variation in magma viscosity, which is defining rate of supply. So the lower is the viscosity, the higher is the rate of supply. And crustal rheology. The colder and the stronger is the crust, the more tendency for vertical propagation we will have in our intrusions. So this is what single model tells us. And recently, Tobias Keller, in his PhD thesis, he did full two-phase flow intrusion emplacement models. And in fact, actually, they do agree quite well with prediction from single phases. So it's approximately kind of the same. Cold geotherm and mafic lower crust, they're promoting vertical intrusion emplacement, whereas hot geotherm and then more ductile lower crust are promoting horizontal spreading of the intruding magma in the lower crust. So more or less these simplified single-phase flow models published in 2007, they do seem to correspond what is happening in two-phase flow systems. So what is happening in 3D, of course, you get lots of pipe-like geometries if your magmatic channel is localized. So you may have like this type of complicated topographies on the top and brittle plastic deformation accommodating volume of magma intruding into the crust. So another example where we also use magmatic weakening as strain weakening. And this one applies to Venus because it's a planet of plume lithosphere interactions. I have another 10 minutes, so it's okay. Then we have lots of these circular structures which are called corona and nova. We have 64 nova structure, which are some centers, which are not volcanoes. In reality, these are tectonic structures. Sometimes there are some volcanoes surrounding them, but it's a hill which is dissected by radial tensile fractures, possibly actually filled by dikes, because they have different reflectivity in radar images. And they may have very different morphology. There are some of the rises, then central rise with a ring, then there are some different plateau-like or even flat novae structure. Then, in addition to that, there are 512 corona structure on Venus, which are circular, annular structure. Typically, origin of these structures explained by flexure of the lithosphere due to the plume lithosphere interaction. But I really wonder how you can flexure the lithosphere that some of parts of this corona looks like mobile belt. So it looks like there is lots of compression here. They really look like strongly deformed. It's not really flexure. Some of these parts, you know, you can think about flexures where it's just gently fractured. But here there is too much deformation apparently to think about them as flexure. So I do think that it's mostly tectonomagmatic structure formed due to the melt percolation from the plume interacting with the lithosphere. So many of them, they have quite funny morphologies. This is what I would think is a fracturing pattern. So gentle fracturing under, you know, some pressure induced by vertically propagating structure. The only trouble is this is only 100 kilometers across. Then if it's a big plume, actually very difficult to imagine that with the lithosphere it can create structure which are as small as that. In addition, they are part of big clusters, as you see. And you have a cluster of structure. Probably this big structure is formed by the plume. But then what are those small structures forming within this big ring, which is 1,000 kilometers across? And there is a structure such as Artemis corona, which is almost 2,000 kilometers across, with lots of complicated things happening in the middle of this structure, and then belt, which was sometimes interpreted as some kind of subduction zone on Venus. So what I would like to show here are 3D high-resolution thermomechanical models of this corona formation. And then we use here strain weakening, which imply that transmagmatic fluids or melts traveling through the lithosphere, and as soon as we create some fracture zones, they can become very quickly weakened by percolating melts. So we have this plume, which is not very big, only 200 kilometers across, interacting with very warm and thin lithosphere. So initially what we see is broad dome-like structure, radial pattern. In the middle there is nothing, no fracturing at all. And then this looks like, to some degree, like arachnoids which are found, so really a flexure. As soon as plumes start to penetrate through the thin lithosphere, melts are expelled from the plume. They are computed to percolate through this to this lithosphere-astenosphere boundary and then pond and form some plume-derived magma region which start to interact with the crust. Crust start to melt under the action, and then since crust is hot, temperature at the surface is 500 degrees C, we start to induce some kind of secondary convection cell within the crust, which is very hot and easy to melt. And then actually our deformation is focusing within the nova rise, and then this nova rise in terms of radial fracturing pattern looks really like this nova. So further on, convection cell propagate closer and closer to the surface. Brittle lead on top of the crust is very thin because crust is very hot and temperature on the top is very hot. And then this crustal convection cell can actually break the lid, and what is happening is start to flow over the surface. Surface bent down, so we start to observe here some concentric fracturing, which are normal faulting. Here we have thrust belt, and then in the middle we have some kind of a rise. And then actually penetration of this crustal plume towards the surface, and hence cooling from the top, and then after some time it starts to dies out because heat of the plume is quickly transferred through the crust. So then after some period of time what we obtain is just a skarn, which is a flat nova structure with no actually visible activity, and then plume accreted to the lithosphere, and then crust which is entirely inactive but with this frozen crustal convection pattern. If we compare what is computed within numerical experiments with what is observed, even some details like this central depression are reproduced. And the reason is you have piercing structure, and then the biggest extension is in the middle on top of it. Then you have just depression. It's not, it looks like volcano and crater of the volcano, but it's not. It's just a depressional structure on the top of the piercing, possibly this intrusion-like crustal convection cell. And also morphology of the coronae obtained in experiments is also looking similar to some of the morphology of coronae observed there. So for example, here I can in principle interpret this belt as a compressional belt due to the propagation of material from the interior of the corona towards the margin, while this region which is faulted I would rather interpret as outer ice with normal faults, which is to some degree similar to subduction zone, but it's not lithospheric subduction, it's just upper crust kind of subduction into the rest of the crust. Also, such type of superstructure can be potentially formed above very big plumes, because instead of magma pond, you form magma ring on top of such plume structure, and then several magmatic centers can arise, and possibly each of them is leaving this corona. Now I have 4 minutes to explain you another implication, and here it's a bulk weakening, bulk magmatic weakening of the lithosphere. In fact, actually, since 2010, we also use in numerical models weakening of the lithosphere above the spots of melt extraction. So if we model crustal growth, melt extraction, and deposition, we are lowering strength of the lithosphere in the column between melt generation and melt deposition. So once again, present day Venus is one good example of such type of behavior, probably. So with, I call this plume-lit tectonic regime, because we have 1 order of magnitude more plume-related structure on Venus than on Earth. And moreover, in this strange regime, you can form something like oceanic-like domain with thin crust and low topography, and continental-like domain with thick crust and high topography. And also even some motions of the cratonic-like domains are predicted on the basis of observation. And even more, even some felsic crust is interpreted on the basis of observation of this pancake, so-called pancake structure. They are too viscous to reflect basaltic magma intrusions or eruptions. They look like really felsic domes expanding on the surface of Venus. So this plume-lit tectonic regime is a tectonomagmatic regime. So to model it, we have to also explicitly take into account crustal growth processes. And this is what we do if we want to model Venus, or if, as some people suggest, if we want to model Venus-like Precambrian Earth. So, and the first implementation of this bulk weakening shows the following. As soon as you have lots of melts under the lithosphere, a new crust is formed, lithosphere is massively weakened everywhere, then plate tectonics disappears. This is one of the predictions of such models. Also, it holds in 3D, increase in temperature, increase in intensity of this magmatic weakening of the lithosphere, change regime quite entirely, and then it forms something that looks more like plume-lit tectonic. I will run for you, at least part-time, this one of the tectonomagmatic models, if it runs. Yes, exactly. So it's just to show you what type of development will be characteristic if we have melts traveling here and there, depositing material in the bottom of the crust, and then actually leaving also some volcanic crust on the top. So we are starting from very uniform mafic crust. Then our partially molten mafic rocks can differentiate, release some felsic melts, and then with time we are reworking this crust in the middle into something that is both felsic and mafic. Moreover, with time you can accumulate domains with more continental-like crust formed by differentiation, both magmatic and mechanical, because you're losing preferentially some fragments, mafic fragments of the crust because of eclogitization at the bottom of the crust. And then with time our uniformly mafic crust everywhere start to be differentiated in some places. And actually what you also start to observe after some tens of millions of years, after many delamination and dripping episodes, that part of your domain becoming more oceanic-like, so with more mafic crust here, and even some kind of spreading center forming at the left. And then another part of the crust is becoming more felsic, with preferential losing of mafic green stuff into the mantle, and then actually it's becoming more continental-like. So it implies that these tectonomagmatic interactions, they do not always imply vertical tectonics. And then due to this tectonomagmatic interaction and due to mechanical and magmatic differentiation, you can get oceanic-like domains, you can get ultra-slow spreading, and continental-like domains within the same framework. So this Venus with continental-like domains and oceanic-like domains, in the absence of plate tectonics, is not a surprising feature. You can see that you have oceanic spreading, which is ultra-slow, happening with, less than a centimeter per year in the absence of any subduction, because some of the material is just simply lost on the other side into the mantle, and this is what is providing shortening in one part and then extension in the other part. So this is what these tectonomagmatic models are predicting. So differentiation and then ultra slow spreading and accumulation of the felsic crust, so continental-like domains. In 3D, you also see that there is a decoupling because of this low viscosity lower crust and between deformation in the mantle, which is subjected to sheet-like delamination episodes, and vertical tectonic in the crust. Sometimes they're coupled, so there are cylindrical lithogitic drips and so on. So this is what I call this plume-lit tectonics regime. And finally, we are coming to the another type of bulk weakening implementation of lithospheric weakening. It's a transition from plume-lit tectonic, which is presumably active, was presumably active in Archean, toward plate tectonic. So we have to initiate subduction in such regime. We can form oceans and continents in such regime. But how do we initiate subduction? Present-day subduction initiation mechanisms are useless because most of them are because of the acting plate tectonic. So we need something else. And something else is probably this plume-induced subduction initiation. And plume-induced subduction initiation, which was studied by one of my master students back in 2008 and suggested on the basis of numerical models, is a penetration of a plume and then initiation of retreating subduction. But for penetration, you need local weakening of the lithosphere, which is implemented as magmatic weakening. So low long-term reduction in the strength of the lithosphere. This was a toy model in reality. And I would never believe in 2008 that there will be evidences that such process take place on Earth. However, in 2014, Scott Wotton and Bob Stern, they published actually a paper inspired by numerical models that they see transition from plume geochemistry towards subduction or arc-like geochemistry, and then actually initiation of Caribbean subduction could be related to the activity within the large igneous provinces, where, by the way, the hottest rock were discovered from among the hot spots, so they even found gorgonocomatiites within this plume region, so this Caribbean large igneous province. So then actually we suggested that this is probably how on Earth subduction and plate tectonic was initiated, and this place in Caribbean is serving as an example how plate tectonic started on Earth, which is of course very vigorous speculation, but we like to do this speculation. So what we do now in 3D, it's a plume, and then on top of the plume where magma is percolating, we are weakening this lithosphere. What we observe, if there is not enough weakening, we form volcanic plateau, and then activity decays and plume is just spreading. So if we are dealing with thick crust and thin lithosphere and Archean conditions with lots of sublithospheric melting, then initially we also form a plateau, and plume even penetrates through the lithosphere, but the trouble is, after initiating some kind of a ring-like downwelling, because of the very low strength of the lithosphere, instead of having any subduction, we have these drips, and then we are back to our plume-lit tectonic regime with vertical tectonics, delamination, and so on. So we need sufficiently strong lithosphere to be able to create subduction. So this alternation between drips and plumes might be related also to the observations that we see, provenance, different provenance in TTG rocks, some of them looking more like arc-like, some other are looking more like plume-like. But it's again also speculation. So probably Artemis corona formed by this repetitive retreat and delamination mechanism on Venus. So if we, however, take present-day mantle conditions, thinner crust and thicker lithosphere, what is happening? We initially form plateau. Plume is then able to penetrate through the lithosphere, create funnel-shaped downwelling. However, further progress is actually precluded by ring confinement. In order to have this subduction retreating in all directions, this ring has to be broken, and this is what is happening by some kind of demateriology. Then we have separate leaves which are retreating, and several subduction zones forming within the retreating domain. And we see within this subduction initiation scenario not only subduction zones, but also ridges, transform fault. So it's a rudimentary plate tectonic cell which is forming by this tectonomagmatic interaction. And it's quite important to mention because on Earth, as was, for example, discussed by Berkovici and Ricard, we are dealing with mosaic of plates. So how to form this mosaic is a separate big question. So probably this relationship between plume-induced subduction initiation and start of plate tectonic on Earth are reflected, for example, by this relationship where people suggested subduction initiation at 3 giga-year. Before that, there was a big peak of juvenile magmatism. So, and then finally, I am already 7 minutes over. Subduction styles. And here I will just, tell you final result. If we play with with magmatism-induced weakening and fluid-induced weakening, we have as much changes in the style of subduction as we would think only possible because of plate motion dynamics or plate buoyancy changes and so on. So it might be even important to consider this effect in the present day subduction systems, despite the fact that it's much less massive, very localized in space and time, and then actually it's probably a decoration on the modern plate tectonic style of behavior and not a major process which is shaping out the entire Earth. So now I'm ready with my conclusions, and fortunately there is only one, that melt-induced weakening must exist. Thank you very much for waiting so long.
Right, I don't want to keep people from their wine too much. Do you have just a few quick questions? Jonathan, could you go back to the iceberg slide, please? So,
This one.
No, way back
Previous
when you were
one.
showing a picture of an iceberg.
Okay, iceberg. Yeah, I just heard isotope. No. Iceberg, yes. Iceberg. Too much pictures. It's typically for Modera, they have too much pictures. But I hope I also gave you some theory. Yes, excellent.
So, for the iceberg sticking out above into the air,
Yes.
I can see how that's occurring because the iceberg is a solid and it transmits
Yeah.
perfectly. Whereas for this big liquid stem, I would assume there would be some attenuation of stresses within the compaction length within the fluid. So I'm wondering how you manage to maintain quite a tall structure from into the mantle.
You maintain this high structure simply for the reason because surrounding is too rigid. You cannot do anything with this structure. And then, as you can imagine, if density of this melt or magma, partially molten magma, is less dense than the surrounding material, you will create lots of overpressure of this magma, which will drive it up. And essentially, high of this column is simply regulated by the potential energy balance. So high of the column times density difference, which is say minus or plus 300 kilograms, and then versus 150 kilometers with 100 kilograms. So it means that you can even employ this magma, which is very dense, on the surface. So you have enough potential energy because of the thickness of the lithosphere. And iceberg effect is because of the rigidity of the surrounding, not because of rigidity of magma itself. So it's anti-iceberg.
Do you have any further questions? In which case, can we discuss this all over wine?
Yes, absolutely.
Thank you, Harris, once again.
Thank you.